as I had told you last time, we will first talk about circuit laws and then we will see how these are useful in network analysis. Yes.
The last lecture you had given an example about a fuse.
Yes.
How does that, what is the reasoning behind the resistance going to infinity when the fuse blows up?
Oh, the resistance goes to infinity when the fuse melts. The heat generated is so high that the wire melts.
Yeah, but then you can't, that law won't be applicable.
Which law? Till the point of melting, yes. The heat generated is so high that it melts and therefore causes a discontinuity. The resistance becomes infinite.
So that discontinuity is there in the resistance law?
Yes.
So
when it becomes discontinuous, then the power generated is zero.
Only after it melts does the resistance become infinite. It doesn't become infinite.
At the point of melting, we are talking of 0 minus and 0 plus. And this relationship is only a model. It's not the actual situation. It's a model. But this is a way to see how the fuse melts. After the fuse melts, the resistance becomes infinite. Alright? And it gives the current at which it melts. Okay, any other question on the previous lecture? Alright. I had explained to you the difference between a circuit and a network. A network may or may not contain a circuit. A network is a broader term than a circuit. Network may contain more than one circuit. It may also contain elements which are not parts of any closed path or any circuit. The basic tools for network analysis are due to Kirchhoff's current law and Kirchhoff's voltage law, and as you know already, Kirchhoff's current law is an expression for continuity of charge. Continuity of charge. That is, in a dynamic situation, charge cannot accumulate at any point in the network, and this is expressed in terms of Kirchhoff's current law. That is, if we have a node, any point in a network where two or more branches meet is called a node. If we have a number of branches like this meeting at this point, through some currents arrive at the node, through others the current leaves the node, and let us say these currents are I1, I2, I3, I4 and I5, then you know KCL means that the total current entering I1 plus I2, total current entering must be equal to the total current leaving, that is I3 plus I4 plus I5. So that over any period, any interval, the total charge that arrives at the junction leaves the junction, and this is an expression for the continuity of charge. KVL, Kirchhoff's voltage law, on the other hand, is an expression for continuity of energy or conservation of energy. Continuity of charge is a correct expression, but continuity of energy is not a grammatically sweet expression. It is better to say conservation, or you use both. For both you use conservation of charge and conservation of energy. KCL is an expression for conservation of charge, KVL is an expression for conservation of energy. Sometimes KCL is stated in terms of algebraic sum, which means that each current shall then be given a polarity. It is either positive or negative. Now, any current that enters the node can be called positive, although there is nothing sacred about it. It can also be called negative, but you must be consistent. Namely, if a current arriving at a node is considered positive, then the current leaving the node must be considered negative, or vice versa. So that this relation that I wrote here could also be written like this: I1 plus I2, both are positive, I3 leaves, and therefore I3 is to be with a negative sign, similarly I4, similarly I5, and this gives you the algebraic sum, and therefore this is equal to 0. Symbolically, sometimes we shall simply write sigma I equal to 0. Sigma I meaning the algebraic sum of the currents at a particular node, and this is an expression of KCL. KVL on the other hand relates to a closed path. A closed path. For example, you have, let us say, a battery, a resistance, another resistance here, perhaps a fourth resistance, and perhaps another resistance. This is a network, all right. It contains a number of circuits. This is one of the circuits, this is another circuit, this is another circuit. There are other closed paths. For example, this is a closed path, all right. There are a number of circuits here. A combination of them makes it into a network, all right. In this network, if you take any closed path, for example, the closed path that I have shown with arrows here, if you take any closed path, then KVL states that the algebraic sum of the potential differences or algebraic sum of the voltage drops is equal to 0. Now let us say this battery is plus minus in this direction, and let us say this is V1, V2 with these polarities, all right. Then when you go round the loop, when you go round this closed path, I have to fix a direction. Do I go clockwise or anti-clockwise? Let us say we go anti-clockwise, and minus to plus, that is from smaller potential to larger potential, let us consider that as positive arbitrarily. We can also do it the other way around. Let us consider that as positive, then V shall be considered positive. Whereas V1, this voltage drop, it goes from plus to minus, so it shall be considered as negative, V minus V1. Then when I come here, the third element here, third resistance, from minus to plus, so this shall be considered positive, and this sum shall be equal to 0, all right, which can also be written as capital V equals to V1 minus V2, or any other way that you like. Or we could even have like this, minus V plus V1 minus V2, where we consider positive to negative, that is higher potential to lower potential, as a positive potential drop or positive voltage. That is, we change the convention. Whatever be the convention, so long as you are consistent, there shall be no mistake, all right. So it is a convention. If you adopt this convention, then the voltage drop V, if you go in this direction, it is negative, this is positive, and this is negative, okay. In other words, sometimes we simply say sigma V equal to 0. Now what is where is the conservation of energy implied here? Conservation of energy is implied in this sense that, you know, the definition of potential at a point is the amount of work done in carrying a unit positive charge from infinity to that point, all right. Now if you carry a unit positive charge around this loop, then you start from some point and you come back to the same point, so the total energy consumed must be equal to 0, all right, because it comes back to the same point. And if you take unit positive charge through a potential difference of V, obviously the work done is V, and if you take it in the direction of potential drop, work done is positive. If you take it in the opposite direction, work done is negative, and that unit positive charge or any charge Q, that cancels out from both sides, and therefore you are left with only voltages or potential differences, and this basically is KVL. Did you know of this interpretation earlier?
Yes, sir.
Conservation of energy, all right. So KCL and KVL are nothing unique in electrical engineering or in network theory. They are expressions for familiar familiar conservation laws that hold conservation of charge and conservation of energy. Now let's see how we can use them in analysis of a circuit. We shall go through a series of examples and illustrate how KCL and KVL are useful in solving quite complicated circuits. First, let's take a very simple circuit. Let's say we have a battery V1, a resistance R1, another resistance, let's say R3, and a third resistance R2, and let's say we have another battery V2. A very simple electrical circuit. In this discussion and in a few more, we shall confine ourselves to resistive networks alone. That is, we shall not admit inductances and capacitances yet. When we admit, we shall have to change a little bit, not much, as you shall see later, but it is convenient to consider resistive circuits and constant voltage or constant current sources, that is batteries for constant voltage source or ideal voltage source, and ideal current generators which deliver constant currents which remain constant with respect to time. With respect to time, the voltage is a constant, this voltage is a constant. If we use a current generator, we will assume that the current is a constant, all right. That is, we are considering DC sources, direct current sources, either a battery or a current source. We will also consider only linear elements. Non-linear elements we will bring in later, all right. With these two hypotheses or with these two presumptions, we want to find out everything about this circuit, that is all the currents and all the voltages. There are several methods for solving this, and I will illustrate this one by one. One of them is that you arbitrarily assign two currents, let us say I1 and I2, coming out from the two sources. Then obviously by KCL, this current must be equal to I1 plus I2, all right, because this is a node at which two currents I1 and I2 enter. So the current leaving must be equal to I1 plus I2. Now there are two unknowns, I1 and I2, and therefore it suffices to write two equations and solve for them, and these two equations are provided by KVL. That is, what you do is take this circuit first, this loop V1 R1 R3, V1 R1 R3. Then in this loop, if you consider minus to plus or plus to minus as positive, then you start with minus V1 plus I1 R1, this is the potential drop across R1, plus I1 plus I2 times R3, this should be equal to 0, all right. This is the application of KVL around this loop V1 R1 R3. Is it okay? Which I can write in a slightly different manner. I can write I1 by simplifying I1 R1 plus R3 plus I2 R3 is equal to V1, all right. The second loop now, let us take this loop, that is V2 R2 R3. In an exactly similar manner, you can see that the equation that we shall arrive at is I1 R3 plus I2 times R2 plus R3 shall be equal to V2, all right. So these are the two equations which now we shall have to solve. Let me point out right at this point that instead of formulating arbitrarily two currents like this, we could have formulated a loop current. For example, we could think instead of specifying a current here, I am taking a detour now to illustrate what is known as a loop analysis. Instead of applying KCL to start with, we could assume that I1 is the current in this loop, okay, and we could assume that I2 is the current in this loop. All right. Then obviously the total current in R3 shall be equal to I1 plus I2. So this is another way of looking at it. It's the same thing. This is another way of looking at it, that you formulate instead of branch currents. You see, what I did was I formulated a current in the branch R1, I had formulated a current in the branch R2, and I found out by KCL the current in the branch R3 in the previous method. Whereas instead of that, one could also do like this, one could formulate two loop currents like this, one is I1 and the other is I2. One might ask here, which direction, clockwise or anti-clockwise? This is absolutely arbitrary. There is no set rules, nothing sacred about it. You may set out loop currents in any direction. If finally, let us say I2 comes out as a negative quantity, then you know that the actual direction of I2 shall be in the other direction. That is all. So as far as setting out loop currents is concerned, there is no sacred rule. You could go all clockwise, you could go all anti-clockwise, you could go some clockwise, some anti-clockwise. There is absolutely no problem. Now you see that these equations are the same if we write on the loop basis. You see, I1 for example gets dropped in R1 and R3. So I1 R1 plus R3. Then across R3 I2 also drops, so plus I2 R3, and this is equal to V1. All right. So loop analysis and branch current formulation gives exactly the same results. Is the point clear? We might in some instances formulate loop currents rather than going through branch currents. All right. So our equations are the two equations, I1 R1 plus R3 plus I2 R3 is equal to V1, and I1 R3 plus I2 R2 plus R3 is equal to V2. One of the simple minded way of solving this would be to eliminate one of the variables. There are two variables, I1 and I2, so you eliminate one of them. For example, from the first one you could write I2 as equal to V1 minus I1 R1 plus R3 divided by R3. All right. From the first equation you could find out I2 as equal to V1 minus this quantity, the whole thing divided by R3, and substitute this in the second equation. That is, you could write I1 R3 plus R2 plus R3 multiplied by I2, and instead of I2 you could write this whole expression, V1 minus I1 R1 plus R3 divided by R3, and this whole thing is equal to V2. Now in this equation only I1 is the unknown, and therefore you can solve for I1, and once you solve for I1 you could find out I2. This is the method of elimination. However, if you have more than two loops, let us say you have 50 loops, a power system network in which there are 50 domestic consumptions, and therefore there are 50 loops, then the method of elimination becomes extremely troublesome and tedious, and therefore you need an alternative and a simpler method, and this simpler method is offered by the so called method of matrix equation solution. Okay, matrices. Are you acquainted with determinants in matrices? Fine, that's wonderful. Then we can go smoothly. Let me write down these equations. I1 R3 plus I2 R2 plus R3 is equal to V2. All right. So in matrices we write this equation in the form of a single matrix equation, that is we write R1 plus R3, first the coefficient matrix R3, then R3, then R2 plus R3, this matrix multiplied by I1 I2, a vector, a one column matrix. This is equal to another column matrix, namely V1 V2, and it becomes very simple to solve for I1 or I2. For example, I1 shall be equal to D1 divided by D, where D stands for the determinant of the coefficient matrix, that is D is given by R1 plus R3, 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 R2 plus R3. This is the determinant of the coefficient matrix, and you know how to evaluate determinants, all right. This determinant is a 2 by 2, so product of these two minus product of two R3s, and D1 is the same determinant but with the first row replaced by the right hand matrix, that is V1 V2 R3 R2 plus R3. Now similarly you could find I2 as D2 by D, where D2 is the same determinant but with the second column replaced by the right hand side, that is R1 plus R3 R3 V1 V2. This method is completely general. It is trivial in the case of a 2 by 2 matrix or a 2 loop network, but in the case of a general n loop network where n is greater than 2, it is a mechanization of solving a set of linear equations which we get by loop analysis or branch current analysis of a network. This solution is associated with the name of a gentleman by the name Cramer. So we have applied Cramer's rule. Difficulties arise, however, if we have, instead of only voltage sources, let us consider a difficult situation. If we have a combination of voltage and current sources, let us see what happens. Let us say we have a battery of 50 volt, 12 ohm resistance, then a current generator 3 ampere, and then a 2 ohm resistance, 5 ohm resistance, and to make things complicated we have another bridging resistance here which is 10 ohms. Have you been able to draw? And you want to find out, let us say, this current. Let us call this I5. That is the current in the 5 ohm resistor, or any arbitrary current, it does not matter. We will solve the network completely. What is the problem here is that branch current formulation works perfectly all right. You can formulate currents in the two branches, currents here. This current is a constant current source, so this is known 3 ampere. But if you used to formulate loop currents, then there is a problem, because this is a current generator.
That middle one is current generator.
Unfortunately. Well, that is a practical situation, that there can be mixtures of voltage generators and current generators. There you have to be a little careful. For example, you can see that you can formulate 3 loop equations. Well, you could do that, except that, well, if you formulate a loop like this and a loop current, let us say I1, obviously and a loop current here I2, alright. Obviously I1 plus I2 shall be equal to 3 ampere, minus 3 amperes, quite so. However, do you know the voltage difference across this? You don't. You don't know the voltage across the 3 ampere source, because a current generator can deliver a constant current irrespective of the drop across this, and the drop across this cannot be determined by simply looking at the current generator, and therefore you cannot write a loop equation, you cannot write a KVL around this loop. Is the problem clear? You cannot write a KVL around this loop, and therefore the better strategy is that you do not formulate loops. What you do is you formulate branch currents. Then you will see how simple the problem becomes. Let us say this is I1 and let us say this is I2. Then you know that I1 plus I2 must be equal to 3 amperes. Isn't that right? Minus 3 amperes, alright. I1 plus I2 shall be equal to minus 3 amperes. Alright. And if this current is, let us say, I3, you have to formulate a current here. If this current is I3, then obviously I5 is known in terms of these 3 currents, right? What is I5? I3 minus I2. And you also know I2. I2 is not unknown, because I2 plus I1 is minus 3. So I2 must be equal to minus 3 minus I1. Alright. And therefore how many currents are unknown? Only 2. And it suffices to write 2 loop equations. Now, carefully avoiding the current generator. The current generator must not be inside a loop. So what is the choice? The bigger loop. Well, you can go like this. This is one loop, and the other one is the upper loop. Okay, 2 loops which do not contain a current generator. That is enough, because there are only 2 unknown currents. Oh, why is it minus 3? Because the 2 currents I1 and I2 come here, and 3 also comes here. So I1 plus I2 plus 3 equal to 0, and therefore I1 plus I2 is minus 3. Alright. Once you are able to do that, then you can solve this circuit. Alright. Shall I leave the algebra to you? Okay. Pardon me?
So, this current source,
Yes.
it generates a current of 3 amperes, but not necessarily the current in this part of the, between the 2 junctions, in which between which this current source lies. It's not necessary that the current in this portion is also 3 amperes. So because
This portion.
this is the other portion in which the current source lies.
You mean this node?
This and the below one.
No, I don't understand.
So the segment of the wire where this current generator is fitted,
Okay.
in that segment the current need not be 3 ampere.
What you mean is this current in this part or this part?
In the middle, vertical.
Here. Oh, it has to be 3 amperes.
So but you said that there might be a potential drop across this, and if there is a potential drop,
There would be a potential.
current.
This, when I draw a line like this, it is a 0 resistance line, and therefore the potential drop, just a minute, potential drop in a line like this is 0. The drop occurs across the 3 ampere current source. What is inside the current source we do not know. It might contain transistors, it might contain resistors, and so on and so forth. It may be an electromechanical generator. Across the terminals of the generator there is a voltage drop. The voltage drop does not occur here, it does not occur here. Whenever I draw a line simply like this, it is a 0 resistance line. Alright. So the voltage drop from here to here is the same as the voltage drop from here to here. Agreed? It is a device, and what we have shown is a symbol. Is the point clear?
So there is no effect of the currents coming from the adjacent wires.
There is effect. I1 and I2,
Yes, sir.
these two come here 3 ampere also comes here, and therefore the sum of the 3 must be equal to 0. That is what I wrote here. Okay. Or you can say 3 ampere comes here and divides into 2 currents, minus I1 and minus I2. Alright. There are many ways of looking at it. The figure has become a bit complicated, so let us draw a fresh figure and look at this circuit again. What I have is 50 volt, then 12 ohms, 3 amperes, 2 ohms, 5 ohms. I am not writing ohms, it being understood that the values are in ohms, and 10 ohms. Okay. Now, what I was saying is that you should not formulate loops indiscriminately, because if a loop contains a current generator, then you are sunk, because you do not know the voltage drop across the current generator. So you cannot write a KVL equation. You cannot write a KVL equation for a loop which contains a current generator, and therefore I said the better strategy is to formulate branch currents. Alright, and this is what we did. What we did was we formulated a current of I1 here, a current of I2 here, then I1 plus I2 should be equal to minus 3. Alright, then we formulated another current I3 here, and so this current shall be equal to I3 minus I2, and I said that since I2 can be expressed in terms of I1, therefore we have to solve for only 2 currents, namely I1 and I3, and once we solve for them we shall again get a 2 by 2 matrix equation.
If
Yes.
we consider a resistance in the arm in which this current generator is, sir, what will we take the value of current in that?
Okay. If there is a resistance here, that is a very interesting question. If there is a resistance here, alright, then will the KCL equation be disturbed? No. A current generator by definition delivers a current capital I irrespective of what is connected to it. If there is a series resistance, it does not matter, the current is still I, whatever be the resistance, so long as it is not, there is a degenerate case, infinite. If capital R is infinite, then the current generator is disconnected and therefore no current can flow. Alright. So if there is a resistance in series, then there is no change in the KCL equation at this node. Alright. Even then you cannot write a KVL equation, because you can find this drop, but you do not know what the drop across the current generator is. Alright. Any other question? Okay. I wish to take this same example to illustrate another method of solving the same network, and this method I wish to introduce like this. I will draw the network again, 50 volt, 12 ohms, 3 amperes, 2 ohms, 5 ohms and 10 ohms. In this circuit we argue that if we know, we were trying to solve these circuits for the currents, alright. We wanted to find all the currents. Suppose instead of currents we find voltages at each of the nodes. The voltage here is obviously 50, we know this because it is connected, and this is a common point, this is a zero potential point. We could consider this as grounded or zero potential, alright. So this node voltage is 50, this node voltage we do not know, it is a current generator, we do not know what this voltage is. We also do not know this node voltage, another node, alright. These are 1, 2, 3, 4 nodes, of which 2 of them are known. This node is 0 voltage, this node is 50 volts, This node we do not know, let us call it V1. This node we do not know, let us call it V2. If I know V1 and V2, obviously everything else in the circuit shall be known. For example, the current in 12 ohms shall be 50 minus V1 divided by 12, or the current in 5 ohms shall be simply V2 divided by 5. So all currents shall be known if we know all the voltages, and this is called the node voltage method of solution. Node voltage. Instead of loop currents or branch currents, we solve for node voltages, and we apply basically KCL here. We do not apply KVL because we are not going round a loop. Alright, we apply KCL. Now, to be able to apply KCL, and we are solving only for V1 and V2, so we need to write only two node equations. At this node, the currents that are leaving this node are V1 minus 12 minus 50, V1 minus 50 divided by 12. Alright, this is the current that leaves in this direction, plus the current that leaves in this direction is V1 minus V2 divided by 2, alright, and the current that comes to the node is equal to 3. Is that okay? This is an expression for KCL. Alright, the current leaving in this direction, current leaving in this direction should be equal to the sum of these two currents, should be equal to the current coming. I could have written this with minus 3 equal to 0, but I have written it with 3, which if I well, let us go to the other equation. The other equation is will be at node 2, V2, and you see the currents that are leaving this junction are firstly V2 by 5, then plus V2 minus V1 divided by 2. This is the current that leaves V2 and goes towards V1. Alright, V2 minus V1 divided by 2, then plus there is only another current which is V2 minus 50 divided by 10. This should be equal to 0. There is no current generator here. Alright, and therefore if we clear this of fractions, we shall get two equations in V1 and V2, which we can now solve for. Do you want me to carry out this algebra, or we can skip it? I want to know the answer though next time. Okay, would you solve these two problems and let me have the answer next time. We have therefore learned of three different methods, actually two methods for solving networks. One is the loop analysis and the other is the node analysis. In loop analysis, we encountered situations where a loop equation cannot be written if there is a current generator in the loop, and therefore what we did was, in those situations we formulated branch currents. If there are no current generators in loops, we could formulate loop currents. So there are two methods, one is the branch current and the loop current. The branch current method always works, the loop current method may not work if there is a current generator. Alright, one has to take stock of the situation and decide the strategy. It is exactly like when you are at a crossing, at a complicated crossing and you are driving, then you have to take an instant decision which way you will turn. Alright. In node analysis, instead of concentrating on currents, we concentrate on node voltages. Alright, and we write basically KCL equations. In loop analysis, we take help of KVL equations. That is, the determining equations for currents in loop analysis are KVL equations. The determining equations in node analysis are KCL equations. In loop analysis we solve for currents, in node analysis we solve for voltages. Either method is okay for a given situation, but as you shall see later on, one of them shall be preferable in a given situation. In a given situation you might have to work less with node analysis rather than loop analysis. Alright, is the point clear? In one of the methods, yes.
In node analysis, how do we know which terminal is to be grounded? Which point is to be grounded?
Usually wherever the source is, one of the terminals of the source is assumed to be grounded. It really doesn't matter because you are talking of potential differences, and therefore any point can be taken as a reference. Let me give you an illustration. Suppose we have a network like this, the same network but not with a current source. Let us say another resistance like this, and then you have a source here you have a source here plus minus. Well, it could be current source or voltage source. That is why I have not shown anything. I have not shown it as a battery or a current source. It could be any source. It means that if it is a current source and the current goes in this direction, if it is a voltage source, then this is positive polarity, this is negative polarity. Any direction, it does not matter. You have another resistance here and you have a resistance here. Alright. Now can you tell me by looking at this circuit which method you shall follow, loop analysis or node analysis? Loop. If you follow loop analysis, well, the answer is incorrect. If you follow loop analysis, you see you formulate 3 loops, you shall have to write 3 equations. On the other hand, if you take node analysis, then all that you have to do is to find these 2 node voltages, V1 and V2, and therefore one shall consist of a 3 by 3 matrix, determinant of 3 by 3, and the other shall consist of 2 by 2. Obviously node analysis shall be preferable in this context, and this decision you have to make.
Excuse me, sir.
Yes.
So this is a current source.
If this is a current source,
And what will be the potential at the positive terminal of the current source?
yeah. Okay, he got me. I was expecting this question earlier. If this is a current source, obviously this loop equation cannot be written. So what do? If this is a current source,
Convert it into voltage source.
then convert it into a voltage source. No, there is nothing in series with this. So all that you know is now you cannot formulate loop equations. This loop equation cannot be written, and therefore what you do is, if this is a current source, now we are going to a different situation. Alright, if this is a current source I, then you formulate 2 branch currents, let us say I1, and this shall therefore be I minus I1. Alright, similarly I1 comes here, breaks up into 2 portions. Okay, similarly I minus I1 comes here, combines with this current and flows through this. So you write all the branch currents, then you have to write only 2 loop equations. Is the point clear? Yeah.
So if you follow like node analysis, then sir what will you take the position?
If we follow node analysis, okay, if there is a current source and this is the node, then obviously, well, then you have to write 3 node equations. Yes, you have to find out V3 also. And in that situation, if you have a current source here instead of a voltage source, which method shall you prefer? Obviously loop analysis. This problem clearly illustrates that depending on the source, this is why I did not specify the source to start with, depending on the source and the architecture of the network, one of the 2 methods shall be preferable, either the loop analysis or node analysis. But you have to exercise a little bit your gray cells to be able to come to the decision as to which method you shall follow. If you follow a wrong method, you will spend more time. You may get the correct results at the end, but you will spend more time. And for an electrical engineer, for an engineer who has taken 110N from SCDA, this should not happen. Alright, you should be able to decide right away which method you shall follow. Spend 2 minutes on this, then you will save 20. Okay, it is worth spending this time. Alright, we shall work out a very large number of problems on loop analysis and node analysis. In fact, throughout the course we shall be solving loops and nodes only, whether it's an electronic circuit or a passive circuit. This is what we shall do. Now we go back to the question of ports. I introduced the concept of ports yesterday, and I said that if I have a network which has 2 terminals only, then you say it is a one port, and therefore all you can do is you can connect to this either a voltage source or a current source or any other general network, okay, any other one port. You can also connect any other. Now this is the most general connection. This is a one port and this is a one port. Let me use this color. Alright, 2 one ports can be connected to each other. Now it may turn out that each of these one ports may contain a source. Alright, one or more sources. And under that condition, one can say that this one port is driving the other one port. You can consider like that. Or you can say there is nothing sacred about the left one driving the right. You may say the right one is driving the left. Alright. In such situations, one of them is considered as a load and the other is considered as the driver. There is nothing sacred. You could consider this as the driver, this as the source, provided this contains an active element, a battery or a current generator or a combination. But suppose I have, let us say, the same network that I had drawn. Okay, if this is my first one port and this is my second one port, obviously the left one is the driver, the right one is the load. Alright. Now whatever be the composition of the 2 one ports, it turns out that in so far as this current is concerned, let us say I, alright, in so far as this current is concerned, the one port to the left can be replaced by an equivalent circuit. The one port to the left can be replaced by an equivalent circuit, and this circuit consists of a voltage generator Vt in series with a resistance Rt. You understand what I mean? It turns out that the one port which you consider as the driver can be thrown out and replaced by this simple series connection of a voltage source in series with a resistance Rt. In other words, I shall be the same whether you connect this one port, actual one port, or its equivalent circuit, and it is in that sense that this is an equivalent circuit. Alright, and this concept was first given by a gentleman named Thevenin, and this is called Thevenin's theorem. Let me state this formally. Thevenin's theorem states that in so far as the load current is concerned, one of them can be considered as a load, the other can be considered as the driver, and Thevenin says in so far as the load current is concerned, an arbitrary 2 port can be replaced by an equivalent voltage source in series with an equivalent resistance. The subscripts T should be clear. T stands for Thevenin. The question is, what is VT and what is RT?
It's an arbitrary two-port.
It's not a two port, it's a one port, an arbitrary connection of a one port to another one port. In so far as the load current is concerned, the one port can be replaced by an equivalent voltage source in series with an equivalent resistance. The values of VT and RT is already 356, we shall consider on Friday.